This is one of a series of lectures given by the Further Mathematics Support Programme for A-Level Maths Revision. In this lecture we'll be looking at the Edexcel Decision Maths 1 specification, and in particular minimum spanning trees. The specification says that you should know Prim's and Kruskal's algorithms to solve problems for minimum spanning trees. To remember the difference between these, try and remember that Prim's algorithm starts at a point and then the tree grows from that point. So starting at the point, we look for the smallest arc coming from that point and add that into the tree. You then must then look at both points that are available to see where the next smallest arc comes from. At every stage of Prim's algorithm, the diagram that you have is a tree. Kruskal's algorithm, on the other hand, works in a different way to give the same answer. This says start off by using the smallest arc and then progressively add the next smallest arcs to your diagram. It's not necessarily going to be a tree all of the time. It doesn't have to be connected even, as in the diagram at this stage. But eventually all the points will join up so that you have a spanning tree for the graph. You should also be aware that networks graphs can be represented by matrices, so a table of values, and you should be able to draw the network from a given table, and also to use Prim's algorithm in its matrix form. So in a couple of questions now from exams to illustrate all of these points. I'll look at the first question so that you understand that there are certain things that you have to be able to define in exams. A connected graph is the first thing that we're asked. Now, a connected graph is where every pair of points has a path between them. So for every pair of points there is a path between those points. A tree is a graph with no cycles. That's the important thing to get in when you're looking at the definition of a tree. It says no cycles. A spanning tree is obviously a tree, but it's a tree which includes all vertices of the graph. Finally, in this question, the question was talking about Prim's algorithm. We're asked to name an alternative. Obviously, they're expecting you then to be able to just quote that the alternative algorithm for finding minimum spanning tree is Kruskal's algorithm. The mark allocation for that question was very, very simple. Just a single mark for each of the definitions, making sure that you had the correct words in there. This slide shows the page from the specification, which is the glossary for decision mathematics. So you should really know all of the definitions that are here, not necessarily word for word, but be able to get the essence of them written down should you be asked them. Particularly the ones that we just looked at there: a tree, a connected graph, a spanning tree, which includes all the vertices. And then a minimum spanning tree, is one which is of smallest weight. So we've got all sorts of definitions you may be asked. The idea of a cycle came into the tree. So a cycle is where we have a closed path. And that was further up there, the cycle. The path is just edges going from one thing to another. All of those may be asked in the context of the minimum spanning tree questions. Here's a question using a table or matrix. We're asked in this question to use Prim's algorithm starting at London. So we're given this particular point to start at, and that will always be the case when you're using Prim's algorithm, to find the minimum spanning tree for these cities. It says you must clearly state the order in which you select the edges of your tree and the weight of the final tree. So what the examiners are looking for when they're marking this particularly is the order of the selection. You might also include in your write-ups, not in a matrix way in this one, in this question where the order will be specified, but in other questions where you're not using a matrix, there may be a choice. And also there'll be situations where you can't actually use a particular edge because it would produce a cycle. The advantage of using the matrix method is that a cycle cannot actually occur because of the way the method works. So we're starting off with London. What I tend to do is to indicate that on my matrix with an arrow. And then we would look at taking out the row for London from the matrix, so deleting that whole row. We then look down the column for London to find which is the nearest city to London, and in there you can see that Oxford is the nearest one. So this would be our first one that we're going to put in. So we'd indicate over here that we've gone from London to Oxford, and that is length 56. At the same time as doing that, I would also be looking at completing the diagram. So what I'm going to do now is just change the slide so we can see the diagram that you're expected to do in the answer book. So here we are on the diagram, and all we need to do is connect London to Oxford 56. You might as well do that at the same time as completing the table. So we've now reached Oxford, or we have a connection to Oxford, so we can delete the row for Oxford. This is the thing of this algorithm which stops cycles occurring, because we're not going to link back into that one again from another point. We can say that okay, now that Oxford is on our tree, we can indicate it at the top, because when you're using Prim's algorithm you should look not just at Oxford, which is the point we've reached, but at all the points which are currently on the tree. So that includes London as well. So we now look down the columns to see which is the closest to either London or Oxford, and we see that in fact it's Cambridge at 60, and that will be the second point. So we're going to link London to Cambridge as our second point and put that on our diagram, London Cambridge 60. So again, we've now reached Cambridge. Get rid of the row for Cambridge, but indicate that it's part of the tree at the top. So we're now looking at 3 columns: Cambridge, London and Oxford, and the third point is 62 away, so Norwich 62, that's our third point. So we've linked Cambridge to Norwich with a weight of 62, and we can indicate that on our diagram. Norwich is now part of the tree, so delete the rest of its row. but indicated is in the tree at the top. So we've now got 4 columns that we're looking at, and we're looking for the next one to join us, and we'll see that in fact that's 63 is Salisbury. So we've gone from Oxford to Salisbury, length 63, and again worth putting it onto the diagram, Oxford to Salisbury. Delete the row for Salisbury, but indicate that that is now part of the tree. So we're now looking at a total of 5 different columns, and if you scan through that you'll find that the smallest one here is at 43, and that's connecting Salisbury to Portsmouth. So Salisbury to Portsmouth, show that on the tree. Delete the row for Portsmouth, but show it's part of the tree. And then finally we're trying to find to Lincoln York, and we'll see that the shortest distance to Lincoln York is 156 from Cambridge. Now I haven't actually put all of the lengths on the diagram for the tree, not necessarily going to be needed, but I'll put them in just for completeness. And then the question asks us for the total weight. So we add up all of these and we find that the total weight is 440, and of course this is in miles. Well, the marking for this question, though, as a method mark, once you'd indicated that you're doing the right sort of thing at the start, followed by 2 accuracy marks depending on how far you got through the tree correctly. A B mark for the final weight, and then another B mark for drawing the diagram when you'd finished the tree. The next question says we have a diagram representing distance in meters between 8 vertices, and the diagram is in figure 1. We're asked to use Kruskal's algorithm to find the minimum spanning tree for the network, and importantly it says you should list the arcs in the order in which you consider them, and in each case state whether you are adding them to your minimum spanning tree or not. So this is what again the examiners are looking for. Has it been added, or has an arc which has been considered been rejected because, for example, it's producing a cycle? Now in fact what I'm going to do is to look at the question twice, once using Kruskal's algorithm and then just to show Prim's algorithm being used in exactly the same diagram so that you can compare them, although the question itself only asks for Kruskal's algorithm. Well, remember Kruskal's starts with the smallest arc available on the network, so the smallest weighted arc. And in this case it is arc DE. So we're going to include DE, and what I would suggest you do is indicate that on the diagram as well, that that one has been included. It's worth keeping a track of its weight, so that is 18. And then we move on. We can look anywhere on the diagram for this. You do not need to connect it to DE, because in this algorithm, it's not necessarily going to be a tree at every single stage. In fact, the next one is GF, which is 21. Following on, DC is 22. And then the next one is size 24. Now there are two of size 24, DB and CE. But we can't use CE because that would produce a cycle. You can see it would give us from C to E to D and back to C in a closed triangle. But we can then use BD. And that's size 24. The next one is EG, which is size 26. You can see at that stage the graph wasn't connected. It's now going to be connected again. EG is size 26. But then we have the next ones to consider are EF, which is size 28, but we can't use that one because that would produce a cycle, and also CF, which again would produce a cycle. So not EF and not CF, because both of these produce cycles. AC is the next smallest one, weight 30. AB is the next one, but again that produces a cycle, so not AB. And finally GH, which produces a weight of 33. Is added in to complete the tree. Now how do we know the tree is completed? Well, we've got a total now of 7 arcs, and as there were 8 nodes in the network, then there's always going to be one less arc than there is number of nodes. So 7 arcs, so it's now complete. So it's important not just to get the correct arcs, but also to get the correct ones rejected from that. We'll now look at Prim's algorithm. I'm going to start at D again, so that the first one adding in is, as before, DE, and that is length 18. But then we're going to look from either D or E. We're not looking for the smallest arc anymore. We're looking at the arc coming from either D or E. So the tree is going to grow. So the next one to add in is DC. And you can see immediately then that our algorithm has gone in a completely different route. And following on from that, we get DB. So DB size 24. Again, we could have considered CE. Let's do DB next though. Size 24. And then we'll say not CE, because that would produce a cycle. Looking again at every point that we've reached so far, and see what's the next smallest one coming from that, and we see that it is EG of size 26, weight 26. and then GF, which is 21. So you can see this idea then that at all stages we have a tree, and you can look at any single part of that tree for the next ones, 21. We then go through a series of arcs which are going to produce cycles. We've already rejected CE, but now we can look at EF and CF. So EF and CF would both produce cycles. And that's got us up to a weight of 29 with CF. So we then get AC coming in with length 30. We're not AB because it would produce a cycle. And then finally GH. Which is length 33. So you can see that once we've completed, we have exactly the same minimum spanning tree as we had when we used Kruskal's algorithm. The other thing to note is that you don't always get the same minimum spanning tree because they're not necessarily unique. In this particular question, there's only one answer that we can get. However, there are sometimes more than one tree which is a minimum spanning tree for a particular network. The marking for that was again reasonably straightforward. There's M1 for the first 4 correct, and then A1 for all 7, and A1 for correct rejections. Well, that completes this lecture on minimum spanning trees. Other lectures in the series are available, and you can find information about that at www.furthermaths.org.uk.